quiz or the homework assignment?
So for the homework on Friday,
Yep.
how are we supposed to do number 7? The one about the length of the string being L and the speed of the mass?
Do you have it with you? Can I?
Yes.
Oh, okay.
How are you supposed to do that one?
Okay, so that mass, this is,
The homework on Friday.
yeah, Friday, homework number 7. So you have a mass swinging around in a circle. And it tells you that the length of this string is L, and that this angle is theta. And it tells you that the speed at any instant is square root of G, L, tangent theta, sine theta, square root. And it just gives you that, but we'll be able to calculate this eventually. What's the acceleration vector of the mass? So let's put the coordinate system here. Okay. Well, in this picture, I'm just going to draw this in a different view so we can visualize stuff a little better. So here's a view from above. There's the mass. What do we know about the, well, first, what do we know about the velocity direction? Okay, it's going, we have to choose the direction it's spinning. Oh, I guess it's given the other way, isn't it? It's going this way, which means it's going clockwise. Okay, so what's the direction of the velocity vector? Down. And we're given this speed that we're assuming is constant. It doesn't say anything about changing speeds. So what's the direction of the parallel part? What's the direction of the tangential acceleration? There's no tangential. The centripetal is towards the center. So the centripetal acceleration is that way. And since there's no tangential, that's also equal to the acceleration. Okay. So we know the direction is in the negative x. Let's see, with this coordinate system that I drew here, our x-axis goes this way, our y-axis comes out towards us, and then our z-axis would have to go this way. Okay, so if the centripetal acceleration is going toward the center, then the direction is in the negative x. And the magnitude for the centripetal acceleration, there's two ways to calculate that. Either omega squared r or v squared over r. We're not given anything about omega, but we can calculate v squared. So for us, this is the square of this, so G, L, tangent theta, sine theta over r. And can we figure out any more about R? Well, if you look at this picture, this is R. So R is just going to be L times sine theta. So we got GL tangent theta sine theta over L sine theta. Those cancel, and all you have left is G times the tangent of theta. So the centripetal acceleration vector, or the total acceleration vector, is this in the negative x direction. So negative G tangent of theta, 0. Any questions about that? So you're just doing a symbolic, symbolically giving a representation for the acceleration based on what you know about circular motion. Any other homework questions? Okay, so now we're going on to particle kinetics. So far, what we've been doing is called kinematics. I don't know why they made these two words so similar, but they did, so we got to get used to it. Over time, I've learned to come to terms with it, and now you have to start that process for yourself. Kinematics deals with quantities that you can measure from a video. Let's say it deals with quantities you could measure from a video of an object's motion. Those are time, the position vector, the velocity vector, and the acceleration vector. We're still going to keep using these, but now we're going to introduce what I'll talk about as the causes of this motion. And those are mass and force. Mass is easy to introduce. Force is going to take a long time to introduce. But what we're doing in kinetics is we're relating these two new things to the motions that we've been talking about already. So we've been doing all this stuff where we get some information about the motion, and then we can say, okay, based on that, we know what the acceleration is, we know what the velocity is. Now we're going to figure out how to relate the acceleration, the velocity, that kind of stuff, to how hard something is pushing on that chosen object, or how hard something's pulling on it, how hard gravity's pulling on it, that kind of thing. Okay, so let's start with mass. That's the easy one. Mass is always a positive scalar. You can't have negative mass. And mass is the measure of an object's resistance to changes in velocity. So if no other object interacts with your chosen object is just going to always continue in whatever velocity it had before. It'll just keep moving with a constant speed in a straight line forever. How hard it is to get it to deviate from that constant speed in a straight line depends on its mass. So I don't know, have you guys all been to the Science Museum in your lives? The one in St. Paul? Do they still have this thing? They used to have this when I was a kid. So they had this like hunk of metal that they said was a compacted truck. And it sits like on a little cart thing with a button. Does that ring a bell? And when you press this button, it did some kind of air track thing. I don't know. I don't remember what it does. I was a little kid. But what it does is it makes it so there's no friction with the ground. And this has a lot of mass, right? It's a truck. And so even with no friction, when you press that button and there's no friction, it's still hard to make it so when you first press the button, it's sitting there. Its velocity is 0. And to change it from that velocity of 0 is really hard. You push really hard and it starts moving really slowly. But then once it's going, it's just as hard to make it stop. You know, you have this truck going, not very fast, but say like 2 miles an hour. It's just as hard to pull on it and get it to stop. That's because that big mass means that it's very resistant to changes in velocity. Whereas, a ping pong ball or something, it's moving with a speed. It's really easy to make it stop or move or turn or whatever. Okay, well, this example was really useless then if you guys don't know what that is. Okay, that's the compacted truck at the Science Museum. The big mass means it's hard to change its velocity. So more mass for a chosen object means it requires more effort to change its velocity. And changing velocity, we can break up into two things. It requires more effort to make it change speed up or slow down. And it requires more effort to make it turn. These two things together are what it means to change velocity. Either one of these or the combination of these. Okay, so what's the relationship between mass and weight? Mass and weight are not the same thing. For a given gravitational field, like if you stay on the same planet, the mass is proportional to the weight, or I guess I'll say it this way. The weight is proportional to the mass. Weight is the force gravity applies to an object. So it's different for different gravitational strengths. So if you want to, lose weight or gain weight or whatever, that's easy to do. It's expensive. You got to get to a different planet, but it'll work 100% of the time. Not like stupid Nutrisystem or something. Like if you go to the moon, you'll lose 83% of your weight. That's the good news. Mass is not so easy to lose. You don't change mass when you go to different gravitational fields. On the moon, you have the same amount of mass that you have on Earth. Mass doesn't depend on gravity. So in outer space, people don't have any weight. There's no gravity. But they do have mass. And actually, for astronauts, it's really important to get accurate measurements of their mass when they're on a space station or whatever, because it's really easy to lose bone density and have your muscles atrophy. So it's really important that doctors are getting accurate information about a person's mass. But like, how do you measure a person's mass when you can't use a bathroom scale? Because a bathroom scale really measures your weight. It measures how hard gravity's pulling on you. If there's no gravity, that isn't going to work. Anybody happen to know? The only person I think would probably know this possibly is Jay. Have you ever heard about, like, how do they measure mass in outer space?
Don't they
Oh.
have,
Okay, yeah.
okay, don't they have like circular things that spin and they walk on it and it's like they're walking on gravity?
That is, I have never heard of that. I can't say no, I don't know. But the way that I've heard of them measuring it is different than that. Have you heard of a way?
Does it have anything to do with like putting them in a liquid and see? I know it's volume, but does that help somehow?
Yeah, that's volume.
Just volume.
Yeah. Yep.
Couldn't there just be like a plate on the wall they have to push off of, and then just how much?
Yeah, that's good thinking. So that's kind of the principle is, so they have this thing that, like, apparently, I've never seen it, but apparently it just shakes them back and forth. And it measures the force that it's applying to them. And it can measure the acceleration that they're making. Every time they go back and forth, that velocity is changing. And so it's measuring the force required to cause a certain amount of acceleration. And so the relationship comes from the relationship between force and acceleration. It doesn't come from measuring the force applied by gravity. SI units for mass. Are kilograms. That seems a little odd, because you'd think it would be more natural to use grams, since kilo is kind of, that name means 1,000 grams. But no, you don't use grams, so that's just how it is. That's pretty much all there is to mass. But now we have to talk about force, and that's a lot more complicated subject. So what did I say about mass? Mass was the easy one. Okay, so now we're talking about force. That's the hard one. Mass, remember, is a positive scalar. It's a positive number. That means that mass doesn't have any direction or anything. It's just a number. Force is a vector. The magnitude is a measure of the intensity of pushing or pulling. And since it's a vector, it also is acting in a direction. And so we have to, when we do calculations involving forces, we have to be able to calculate the magnitude and we have to be able to calculate the direction. The way we're going to do it in this class is we're going to break down forces into 5 separate types, and each one of those types we're going to know what direction it's pointing, and then we're going to use that known direction to figure out vector components. You can think of force as defined by Newton's second law. Okay, so force is defined by Newton's second law. And Newton's second law is the most important equation that we're going to have in this class. So if you're like, I've been paying attention this whole class, I'm going to take a break right now. No, this is a really bad time. This is the key to this whole class. Take a break, next time we talk about circular motion or something. Okay, so yeah, most important equation in classical physics. And Newton's second law says this. I always abbreviate this N2L. For any inertial coordinate system, and have I mentioned what inertial coordinate systems are before? Okay. An inertial coordinate system means that the origin is not accelerating and the axes aren't rotating. Yeah, maybe in passing or something, but it can't hurt to have it written down again. Okay, so that's a key. Newton's second law only applies for certain types of coordinate systems. Okay? Then the sum of the forces acting on an object, so just write it as sum of forces for now, is equal to the mass times the acceleration. Okay, that's a super important equation. And let me be more clear about what these 3 variables mean. So this one here says the sum of all forces acting on the chosen object. And this idea of choosing a specific object to apply Newton's second law to is really important. M is the mass of the chosen object. And A is the acceleration vector of the chosen object. And one thing to notice about this is that some of those forces acting on the object, and from now on I'm going to call that the net force, so I'll write it as F net. There could be 1,000 forces acting on something. You know, there could be a ball sitting on top of it, and it's resting on the floor, and gravity's acting, and a pelican sitting on the shoulder, and, you know, a helicopter's trying to pull it out of the mud or whatever. All these things could be happening. And we can't say yet anything about those individual forces. We don't know about what the pelican force is or the mud force, but we know that if you add them all up and get this net force, add them all up into this total, this net force has to be the same direction as the acceleration, okay? Because that m is a positive scalar, and positive scalars don't do anything but change the magnitude of a vector, okay? So the sum of these forces, F net, is in the same direction as the acceleration vector. Okay, so let's take an example and think a little bit about what Newton's second law tells us. So let's say that there's so this is kind of the same setup as that number 7 from the homework that I just went through. So let's say there's a ball on a string, and it's traveling in a circular path. And let's say the radius of this circular path is 10 centimeters. The mass is 50 grams. The ball is on a string traveling in uniform circular motion. So what does uniform circular motion mean?
No size,
Yeah, be a little careful, because remember, circular motion always has acceleration, but yeah, it means the speed isn't changing. Okay, but you need acceleration anytime something's turning too, and so you always have that centripetal acceleration making it turn. And so we want to know first, what's the direction of the net force at this instant shown? And second, what are the components of the vector F net? And let's use the same coordinate system that I drew for number 7 in the homework. So there's x, y, z is coming out this way. Oh, and actually, there's more information. I need to give you one more piece of information. So let's say that the ball's rotating this way around the circle, and it's making a rotation every 2 seconds. So 2 seconds per rotation, per revolution. Okay, so first let's just think about the direction. Anybody feel up for trying to do this on the board? Yeah? Okay. That's the enthusiasm I like to see. You're like, yeah, go ahead, go through it. What do we care? Okay. So first of all, I'm going to draw it from, did I choose a coordinate system? Yeah. So I'm going to do it from above. And the direction of motion is like that. There's the object. The coordinate system, there's x, there's z. And the y-axis is coming out. The velocity vector is this way. It's uniform circular motion, so there's no tangential acceleration. There is a centripetal acceleration going that way. And since there's no tangential, that's also equal to the total acceleration. And since the acceleration is pointing towards the center, the net force has to be pointing towards the center too. And we don't know the magnitude of that without thinking about numbers, but we know the direction has to be the same as the acceleration vector. So that means that if something's in uniform circular motion, if you add up all the forces, that sum of forces, the net force always has to be pointing towards the center at every instant. Okay? That doesn't mean the individual forces are pointing towards the center, but if you add them all up, they're equal to a vector towards the center. Okay, so now let's do so this is part A. Now for part B, we'll put the numbers in. The centripetal acceleration is equal to omega squared r, and we figured out that at this instant it's pointing to the left. Omega we can get because we know that every rotation is 2 seconds. So omega is equal to 2 pi radians over 2 seconds. So pi radians per second. And so the centripetal acceleration is equal to pi squared times r, which is, if I'm doing it in meters, that's 0.1 meters. Leave that unit out. And okay, so I'll just write this as 0.1 pi squared pointing this way. And you can recognize that that vector is pointing in the negative x direction and just write it as negative 0.1 pi squared 0. Or you can calculate, think of putting the tail of that vector at the origin of the coordinate system. Recognize that that's a counterclockwise angle of 180 degrees to get from the positive x-axis to the vector. And then it's the magnitude times cosine and sine of 180, which gives you this same thing. Okay. Any questions about turning the magnitude and the direction into vector components? Okay. So now that we have that, we can use Newton's second law. That says F net is equal to the mass times the acceleration. The mass is equal to 0.05. The acceleration is this thing, negative 0.1 pi squared 0. Multiply that through and you get negative 0.005 pi squared 0. Bless you. Okay, so what are the units of this answer? So you can figure it out from this equation. It's going to have units of kilograms from the mass, meters per second squared from the acceleration. So kilograms, meters per second squared. But we use units for force all the time, and that's pretty cumbersome to write. So that's given its own name, newtons. It really is 1 kilogram meters per second squared, but we call it newtons, abbreviate it with a capital N. So this has units of newtons. Yep. Joules is a joule is a newton times a meter, and it has to do with it's an energy measurement. So it has to do with how much energy you put into something by applying 1 newton to it over a distance of 1 meter. Okay, so here's something to notice, something important about Newton's second law. Newton's second law doesn't tell us what individual force vectors are. It only tells us what the sum of all the force vectors are equal to. So it only tells us about the sum of all the force vectors.
So that means theoretically you could have like 2 equally strong, like 3 million newtons applied to both sides, and it would cancel out.
That's right, yeah.
So it would be crushed like flat like a pancake, but there would still be no force being applied.
Right. For a particle, we don't care about crushing and that kind of things because we don't differentiate at all between locations where those forces are applied. So for something to be crushed, it has to have equal and opposite forces acting at different locations. You know what I mean? A particle doesn't have different locations. We're treating it like everything happens at a point. But so, yeah, like right now, there are 2 big forces, pretty big forces acting on me. One is gravity, and one is the floor pushing up. If the floor wasn't pushing up, I would, accelerate. I'd be in free fall. And so those forces are equal and opposite. And so if you measure my acceleration right now, it's 0. But there's 2 big forces counteracting each other. Yep.
And then also, how does mass affect, isn't there maximum of velocity objects can achieve?
Oh, yeah. I don't know anything about that stuff. But yes, so I don't have any background in modern physics. So yeah, all that stuff is super interesting, but I'm not really a good person to answer you about that. But yeah, that has to do with theory of relativity. Yeah, E equals mc squared. That's all has to do with general relativity, and I can't tell you much more than that. Any other questions right now? Okay. So I jumped right into Newton's second law, and Newton's second law is, I said, the most important equation in this class. It makes you wonder what Newton's first law was, you know? Like, why is Newton's second law so much better? Well, so, okay, Newton's first law. It's a perfectly good law. It's just that you can derive Newton's first law directly from Newton's second law, so it doesn't give you any extra information. But Newton's first law says any object with no net force applied to it moves with a constant velocity. Let me say this follows directly from Newton's second law. Which says, if F net is equal to MA, then if you don't have any net force acting, you can't have any acceleration. Okay, so the thing has to move with a constant velocity. And so mathematically, Newton's first law is a result of Newton's second law. Newton's second law, like, this is an unnecessary one. It's redundant. But it's actually a very important intuition to have, and it's something that we all tend to, it's an intuition that people tend to get wrong. And so we're going to do a lab where we just hammer this idea home. It's a really important idea. Not mathematically, because mathematically it's contained in the other equation, but intuitively it's an important idea that we're going to have to develop. Okay, so I said Newton's second law doesn't tell you anything about individual laws that add up to give you the net force. So how do we figure out stuff about those individual forces? That's what we want. How can we use Newton's second law to calculate individual force vectors? And in order to do this, we have to know some things about different kinds of forces that are applied. And so now I'm going to talk about the 5 types of individual forces that we're going to deal with. So you need to know things about the 5 types of forces. these are the 5 types we're going to use for this class. There are some other types, but this is a complete list of everything that you're going to deal with here. The other ones, magnetic forces or electric field forces, that kind of stuff, you can deal with those the same way, but we're just not going to do it in this class. Okay, so here are the 5 types. The first one is weight. That's the force applied to the object by gravity. The second is pushing contact. Who can guess the third one? Pulling contact, yeah. And then friction. And then the fifth one is the force applied to objects by springs. So force applied by springs. In some ways, so breaking it up into these 5 different types of forces and then having springs in there seems a little funny because, like, when was the last time you saw a spring? You know what I mean? Like, is that really as important as weight or whatever? Well, actually, for one thing, it's important in physics problems because it's something you can calculate, and so a lot of problems have them. But for another thing, a lot of materials that are not springs behave in the same way that springs do. Like a big block of steel, that doesn't look very much, you don't think of that much as like a spring. But if you apply gigantic forces to it, it doesn't deform very much, but it behaves mathematically like a super, super stiff spring. It deforms just a little bit according to the laws of springs. And so even things that aren't really spring coils, you can use this mathematical approach. All right, so the first thing is weight. That's the force applied by gravity. Later we'll talk about gravitation when you're a long distance from the surface of the Earth. But for objects near the surface of the Earth, the force due to gravity, or I guess I'll write it as, let's write it as the weight force vector W, is equal to the object's mass times that acceleration of gravity acting down. One thing that's going to be a really important tool as we go through Newton's laws is free body diagrams. And next class period, I'll give you a detailed list of how to do free body diagrams. But for now, I'm just going to draw free body diagrams of everything that we do. And you can sort of pick up what they are. But okay, so free body diagram of an object. I'll always abbreviate that FBD. And so if this is your object and it has a mass of m, the force vector applied by gravity is like that. It's in the downward direction towards the center of the Earth with a magnitude of the mass times 9.81. Okay. All right, so gravity pulls on objects with an intensity proportional to the object's mass. Okay, so gravity pulls on a truck a lot harder than it pulls on a chicken. Okay, so here's what I want you to think about for a second. Weight is proportional to mass. Gravity pulls harder on large things than small things. But we've been spending a lot of time, like in labs especially, emphasizing how if you can neglect air resistance, and for a lot of objects you can and get pretty good results, two things in free fall exactly the same no matter what their masses are. You know, that a ball made of aluminum and a ball made of steel or whatever, they fall exactly the same. Their acceleration is exactly the same. So I want you to think for a second about how you square those two ideas. How can those both be true? Okay? Are they? Did I make a mistake? That couldn't happen. No, it could, but I didn't. And the way I want you to think about it is it has to do with Newton's second law. Okay? So think about the acceleration of a thing in free fall with when something's in free fall, the only force acting on it is the weight. Okay? And I want everybody to put some kind of answer up on the board. It can be stupid, but try not to make it stupid. So think of two objects with two different masses. Let's call one little m and one big M. And say they're both in free fall. So the only force is weight. Okay, so Newton's second law for the mass little m says 0, negative mg, right? That's the weight force, is equal to the mass times the acceleration vector. And we're going to calculate that acceleration vector. So that gives us two equations. The first one says ax is equal to 0, and the second one says negative mg is equal to MAY. So AY is equal to, those cancel, and you just get negative g. So the acceleration vector is 0, negative g. Okay? So the key thing there, the acceleration didn't depend on the mass because the m that the weight depended on canceled with the m in F equals ma. Okay? And so obviously, I mean, if I just use a different, if I represent the mass by big M, the same thing's going to happen. So Newton's second law for the object with big M, the weight is 0, negative big mg. That's equal to big M times the acceleration. And you get, go through the same calculations. You get the acceleration vector is 0, negative g. And so the take-home message is you have different weight forces, but the same acceleration. Okay? All right, so now that we know something about weight, let's go back to this ball on the string example. There are two forces acting on the ball. Let me draw this picture again. Bless you. Okay, so this ball's traveling in circular motion. It's going this way at pi radians per second. And this was 0.1 meters. What else do we know? This is 0.05 kilograms. There are two forces acting on this ball. The first one is the weight, and the second one is a force vector applied by that string. And so what we're going to do is use Newton's second law this time. So remember, up until now, we've only used Newton's second law to calculate the net force, to calculate the sum of all the forces. But now we're going to break up that net force into two forces. One of them we know, and one we don't know. Okay? So we're going to use Newton's second law to calculate the force vector applied to the ball by the string. So Newton's second law says F net, and this time we're going to break that up into, let me draw the coordinate system back on here. So this was X, this was Y. F net is equal to 0, negative mg. The mass is 0.05. Okay? So this is the weight force. Plus the force vector applied by the string. And that's equal to the mass times the acceleration that we figured out before. What was that? The acceleration was negative 0.1 pi squared, I think. And so we get that, we can subtract the weight force from both sides, and we get that the force vector applied by the string is equal to negative 0.005 pi squared plus 0 positive 0.05 g. And that's in newtons. Okay, so even though Newton's second law only lets you calculate, only gives you a relationship between the total force and the acceleration, when you know things about the individual forces, often you can use that to calculate other things you don't know about individual forces. Okay. Follow what I'm saying there? Okay, this is probably the last force type we're going to get to today. So the second type is pushing contact. So when two objects push against each other, the force, that contact force applied to the chosen object is perpendicular to the contacting surface and toward the chosen body, away from the contacting body. So here's an example. If you have these two balls resting on the floor next to each other and contacting each other right here, I'll call this one 1 and this one 2. Each one of these balls has two pushing contacts acting on it. The floor is pushing on it, and the other ball is pushing on it. Okay. So let's do free body diagrams of each of these two balls. These free body diagrams just show every force that's acting on on the whatever the free body diagram is. So this is a free body diagram of ball 1. Okay? So what forces are acting on it?
Gravity.
Yep, that's right. So that, I'll call that M1 times G, the mass of ball 1 times 9.81. And then there's a pushing contact applied by the floor. I'll call that N for normal, and I'll call it N1.
There's the pushing contact with the other ball.
That's right. And that's perpendicular. So let's think for a second about the direction. I kind of glossed over that. So this normal force is the contacting surface you can think of as the floor. Okay? So this force vector applied to this ball is going to be perpendicular to the floor, and it's going to be toward the chosen body, away from the contacting body. The chosen body is ball 1. The contacting body is the floor, so it's perpendicular to the floor, toward the ball, away from the floor. So that's how we got that direction. The contact with the other ball is perpendicular to that. The surface here you can think of as tangent to where those balls are in contact. So it's perpendicular to that contact, toward ball 1, away from ball 2. And I'll call that R for reaction. You can call that, it can have any variable name you want, but N and R are pretty common. N for normal, because it's perpendicular to the surface. And then, okay, so let's do a free body diagram of ball 2. What forces are acting on ball 2? Yeah. So I'll call that M2G. Then there's the pushing contact from the floor. I'll call that N2. And then there's the pushing contact from ball 1. Now, it's the same contact causing this force, right? That it's the same contact that produced this R on this one. But now, since our chosen body is ball 2, this is toward the chosen body, away from the contacting body, so now it goes this way. Okay? And this comes from Newton's third law, which I'm just going to make this look more horizontal. We'll talk about in depth later, but it turns out that when there's a contact force like this, the pushing contact applied to 1 by 2 is the same magnitude as the pushing contact applied to 2 by 1. So this is also R. Okay, so let's use this idea in a calculation. Okay, so let's say there's an elevator and a kid, let's say on roller skates. Let's say on a skateboard, so I only have to draw those wheels once. Okay, that's a little elevator. The kid is 20 kilograms. And the question is, what's the contact force applied to the kid by the elevator first, if the elevator's at rest. Second, if the elevator is moving up with a constant velocity. And third, if the, I guess I have four. So third, if the elevator has an upward acceleration of 2 meters per second squared. And fourth, if the elevator is accelerating down at 2 meters per second squared. Okay, so I'm going to start with a free body diagram of the kid. It's going to show all the forces acting on the kid. Well, it's actually the kid skateboard complex. Okay. So what forces are acting on the kid? Yep. So that's 20G acting down. And we only know one other kind of force, so what?
The pushing force?
That's right. And then the ground is pushing up on the wheels. Okay, that's a contact where the two things are pushing against each other. They're not pulling on each other. That force is perpendicular to the floor toward the chosen body away from the contacting body. So it's up towards the kid, and I'll call that N for normal. And then Newton's second law says 0, negative 20G plus 0 N is equal to the kid's mass.
Would it be 20 kilograms?
Yes. Oh, right. That's G like 9.81, not G for grams. Yeah, thanks. So the mass is 20 kilograms. The acceleration, what's the kid's acceleration for part A? If he's just standing there in an elevator at rest, this is 0. So you get two equations. The first one says 0 equals 0. That's reassuring. You know, it would be pretty alarming if that wasn't true. But then the second one is where we get some information out of this. Negative 20G plus N is equal to 0. Or 20G is negative 196.2 plus N is equal to 0. And so N is equal to positive 196.2 newtons. Okay. So this is for A. What's going to happen with B? Let's skip that one. Yeah, it's going to be the exact same. And why? Think about why that would be. So B is with a constant velocity moving up.
The acceleration is 0.
That's right. If constant velocity means 0 acceleration and vice versa. So the velocity doesn't have anything to do with these equations at all. The only thing that matters is accelerations. Okay, so now let's go to C. Newton's second law says 0, negative 196.2. That's the weight. plus 0n is equal to 20, and now the acceleration is given as 0, 2. Everyone follow me on that one? And so you get two equations. The first one, 0 equals 0, not useful. The second one is useful. Negative 196.2 plus the normal is equal to 40. And so n is equal to 136.2 newtons. Yes, I do. Indeed, I do. Okay, so, and you know that feeling in the elevator, like when it's just at the, most of the time that the elevator's going, it's going at a constant velocity and you don't feel anything. But for that first, when it first starts moving up, when it's accelerating, you feel that extra heaviness. That feeling is the extra force that the ground is applying, that the floor of the elevator is applying to your feet. And if you were standing on a scale, looking at the scale, for that brief instant that it was accelerating, you'd see the scale, it would look like your weight went up, just briefly. And then when it got back to constant velocity, the scale would say your normal weight again. So what's going to happen in the second case when there's a 2 meter per second squared acceleration down?
It'll be negative 40 instead of positive.
That's right. So here where we have a positive 2, that'll be a negative 2, and it'll end up subtracting from this, and that normal force will be smaller than it was when the elevator was at rest. Okay? Done.